up, my chemistry students? It is Mrs. Thompson again, and today we are talking more in detail about the galvanic cell. Before we do, in little ChemCat humor, it says, I blew up my chemistry experiment. Oxidants happen. Alright, so here we go. This is to help us figure out which one is going to be the anode and which one is going to be the cathode. And so what we need is a table of standard reduction potentials. They are written in terms of reduction. How do I know this? Well, not only does the title say this, but electrons are being added. They are part of the reactant side. And so they're gaining electrons. Okay. So GR. Whichever one is the most positive, that's in terms of the values, will be the cathode. It's the cathode because that is red cat, where the reduction is happening. Okay. The cathode has a stronger pull for electrons, which makes it a better oxidizing agent. So you can see on this table, it's written with the stronger oxidizing agents at the top, the more positive ones are, and then the weaker oxidizing agents are at the bottom. On this side, you see that it's the weak reducing agents at the top and the strong reducing agents at the bottom. Alright, so in this one, if we were to figure out which one is the anode and which one is the cathode, we would look at that table and we would look for zinc and zinc 2+, and copper 2+, and copper. Okay. So here's the table. We have copper 2+, plus 2 electrons makes copper solid. So this is the part that's in solution. This is the electrode. And this is the value, that's potential. Then we also have the zinc solution, the cathode, or excuse me, anode, and then its potential. Now, its potential is negative. So which one is more positive? This one, the copper. And so that makes copper the cathode, where reduction happens, and zinc would be the anode, where oxidation happens. So you're going to have to create a galvanic cell given a list of either a reaction or materials. So in this one, I've given you a list of materials. We have copper sulfate and copper. Now those two, we've got the solid metal and the ionic form. So the copper sulfate would be dissolved in water and form copper ions. So those two would go within the same cell because it's the same metal. Then we have silver nitrate and silver. Well, these both have the same metal in them, so they'll go in the other cell. Then you have potassium nitrate. Now, you might think that that's the ion floating in solution, but we don't have the metal for that one, and so that's probably going to be the salt bridge. Okay. We're going to label the anode, the cathode, the salt bridge, the direction the electrons are flowing, the directions the positive and negative ions are flowing. Okay, so here we go. I just put each solution with its metal into two different cells. And so we've got copper with its copper sulfate, but copper sulfate's broken up. We've got silver with silver nitrate, and silver nitrate's broken up. This is 1 molar in concentration. This is 1 molar in concentration because we're dealing with standard cells. Okay. Right down here you see the oxidation and reduction half reactions. Just ignore that for now. We'll get into that later. All right, the other parts of this setup are the wire, okay, and the salt bridge. So we'll just draw that in. And the salt bridge is going to be made up of the potassium nitrate. So we'll put that inside the salt bridge. All right, so now we have to figure out which one is the anode and which one is the cathode. So we're going to look back at this standard reduction potential. So we need copper and silver. Which one is more positive? That's going to be the cathode. That's where reduction is happening. All right, so that means that silver is more positive. So that's going to be my cathode. So let's label that as the cathode. All right, and then that means that the other side is the anode. The electrons always flow from anode to cathode. So you have a fat cat getting those electrons, eating those up. The ions are going to flow this way. So the positive ion, the potassium in the potassium nitrate, will flow in the same direction as the electrons, and the nitrate, the negative ion, will flow in the opposite direction. Now the anode will be the negative one. It'll produce the electrons, and the cathode will be the positive one. It is attracting the electrons. All right, so there's our first galvanic cell. All right, here's a question for you. What is wrong with this picture? Okay. Hopefully you noticed it is missing a salt bridge, and so the electrons would not be allowed to continue to flow because there's no balance of charge. Okay, here is our second example. We're going to take these two half reactions. Both are written in terms of reduction. How do I know that? That's because they are both gaining electrons. Electrons are on the left side. All right, we're going to figure out which one of these will be the anode, which one is the cathode. We'll predict the direction in which the electrons flow, and then the positive ions, which direction they will flow. And then which one is the positive electrode and which one is the negative electrode. So what do we need? We need the standard reduction potentials. We're looking at lead 2+ and aluminum 3+. Okay, so which one is more positive? Now they are both negative, but lead is actually more positive than aluminum because it's closer to 0. So we're going to pick lead to be our cathode, the one that gets reduced. So we'll label that. Lead is the cathode, which means aluminum is the anode. All right, so the electrons always flow from anode to cathode, so they're going to flow in that direction. The ions are going to flow, the positive ones will flow in the same direction as the electrons, so they're going to flow that way. Those are the positive ions. Now remember, the negative ions are going to flow the opposite direction. We want to know which one's the positive electrode and which one is the negative electrode. The cathode is always positive, just like cations are positive, and the anode is negative, just like an anion is negative. All right. Number 2, identify the electrode that will increase in mass and identify the electrode that will decrease in mass. So remember, it's a fat cat. The cathode gets bigger, it grows, and the anode gets smaller, it shrinks. So the cathode increases in mass and the anode decreases in mass. That's kind of funny. Remember, fat cat. You have to be able to describe the cell using cell notation, and so make sure your copy of this looks good. All right, so cell notation is really simple. It's written in the same way that electrons flow, and that is from anode to cathode. So we write the anode half cell on the left and the cathode half cell on the right. In the middle, we put these 2 double lines here. These 2 double lines represent the salt bridge, or the barrier between the anode and the cathode. On the extremes of this cell notation, you have the 2 electrodes. That's the zinc solid metal electrode and the copper solid metal electrode. To separate the metal from the aqueous, what's in solution, we draw just a single line. So this says phase boundary, or the difference between solid and aqueous. All right, so these are pretty simple. You just have to be able to look at the cell and make one of these. Okay, so we're going to write the line notation for this galvanic cell. This galvanic cell is example number 1. All right, so we write the anode on the left side, and we start with the electrode. So the electrode, the anode, is the copper side. The electrode part of it is the solid metal, so that's going to be copper solid. We're going to draw a line between the phases, so there's a single line here. And then the metal that is a part of this galvanic cell that's actually doing the oxidation and reduction part is the copper 2+ ion. So we'll put that in there. We'll put aqueous next to it. And then we'll draw a double line to separate the anode half reaction from the cathode half reaction, also to represent the salt bridge that's there. All right, so the cathode is going to be the silver and the silver 1+. So the metal and the metal ion. We put the metal ion in the middle because we want the electrodes to be on the very outside, the metal electrodes, the solids. So this goes in the middle, single line, silver solid. Okay, it's really pretty easy. All right, let's write the cell notation for example number 2. Okay. So here we've got the cathode is lead with lead nitrate, and the anode is aluminum with aluminum nitrate. So we need the anode side first, and we're going to put the electrode, so that's aluminum solid. We'll draw a single line. Then we need the ion form. This is Al3+. I know that 2 reasons. 1, I wrote it at the top. 2, there's 3 nitrates. Nitrate's a -1, so this had to be a 3+. So aluminum 3+. And then it's aqueous, the salt bridge, and then we need the lead ion. It's lead 2+, so I needed 2 nitrates, so I can look up here, that's lead 2+. And then the single line, and then lead solid. Alright, that's it. Hope cell notation wasn't too bad. We'll do some calculations on this next time.